Okay, Matt Roscoe here at the University of Montana with a chapter, I should say a lecture to replace my absence on chapter 6-1, which are the number theoretic functions, tau and sigma. Okay, so we're going to handle this chapter in two halves, and so what I hope to do today is in this lecture get through bullet 7. So we'll try to do this much today in this lecture, and then I'll finish the lecture once I'm back with you live on Friday. So that being said, we're going to talk first about what a number theoretic function is, and then we're going to talk about and define the two common number theoretic functions, tau and sigma, give a few examples, talk about how sometimes these things are, I guess, defined using sigma notation, and then I want to show you pictures of graphs of both tau and sigma. And then what I will do is talk a little bit about generalizing divisors, which is an important, I guess, result that we have to first prove before we can actually compute tau and sigma as a function of n. And then I'll actually go through a quick example. So what's a number theoretic function? It's a function whose domain of definition is the set of positive integers. So anything that takes as input positive integers is said to be a number theoretic function. So here is two common number theoretic functions. So given a positive integer n, let tau of n denote the number of positive divisors of n, and let sigma of n denote the sum of these divisors. So again, given a positive integer n, tau of n is the number of divisors that integer has, and sigma of n is the sum of these divisors. So let's go ahead and just sort of take a look at tau of n and sigma of n for n 1, 2, 3, 4, 5, and 6, just as an example, make sure we're on the right track. So I guess if we have n 1, 2, 3, 4, 5, 6, tau of n and sigma of n. Let's see, so tau of n is the number of divisors. So how many numbers divide 1? Well, just 1, right? How many numbers divide 2? 2. How many numbers divide 3? 2. How many numbers divide 4? So 4 is divisible by 1, by 2, and by 4. So there are 3 numbers that divide 4. Just 2 divides 6. And then the big question is 6. So let's see, 1 divides it, 2 divides it, 3 divides it, and 6 divides it. So there's 4. Okay, so sigma of n is then just the sum of these divisors, of which we counted over here. So the sum of the divisors of 1 is just 1. The sum of the divisors of 2 is just 3. The sum of the divisors of 3 is just 4, right? It's 3 and 1. Now the sum of the divisors of 4 are 4 plus 1, that's 5, plus 2 more, that's 7. The sum of the divisors for 5 are 5 and 1, or 6. And the sum of the divisors for 6 are, let's see, 1 plus 2 plus 3. 1 plus 2 is 3. 3 plus 3 is 6. And then we add 6 to that would be 12. And just some observations that you should be able to make right off the bat is what happens when the number is prime. So if we look at the prime numbers in the list, seem to be important. So n is prime. Then let's see, tau of n is always going to be 2, right? Because it's only divisible by 1 in itself. And if n is prime, then sigma of n is just going to be equal to n plus 1, right? Because it's the prime number is divisible by itself and 1, so it's just n plus 1, right? So a couple interesting ideas there. It does seem that, sort of the larger the number gets, sigma of n is going to grow, at least in its ability. So for n, I think the smallest that tau of n can be is actually n plus 1, right? Because you're always going to be divisible by 1 in yourself, but you might have other divisors if you're composite. Yeah, I guess those are the things I think when I look at that. Let's do one more. Let's take a bigger number and just sort of take a look at what this looks like for 36. So if n is equal to 36, let's see, so what are its factors? They are 1, 2, 3, 4. Let's see, 5 doesn't, but 6 does. And then it's 9. So 9 goes with 4, 12 goes with 3, and 2 goes with 18. And of course 36 is in there too. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that tau of 36 is equal to 9. And it turns out that sigma of 36 is going to be equal to the sum of all of these things. I did this in my notes. 91 is the right number there. So you can see once we get to 36, sigma has grown quite a bit, right? Tau of n, though, sort of relatively smaller, and I guess this is because, sigma is summing all the divisors, whereas tau is just counting them. How about one more? What if we did 37 as a contrast? Sorry. Oh, get rid of that too. So if n is equal to 37, then the factors are just 1 and 37, so tau of 37 is just equal to 38, right? Sorry, that's sigma. I mean tau of 37 is just 2, and sigma of 37 is 38. And so quite a difference here. You can see that if we kind of think of the graph of this thing, this is up at 9 and then it bounces back down to 2 at the next input value. It's up at 91 and it bounces back down to 38 at the next input value. So we can kind of think of the graphs of these things right away as being jagged. They are not going to be continuous at all, but it'll be interesting to see what they look like. So you should just be aware that sometimes we use sigma notation for both tau and sigma, and this is just an example of sigma notation where we sum all the divisors of some number n. So that's what the d bar n below means. It means, we take every divisor of some number n and we sum some function of those divisors. So this is a common way of noting, I guess, number theoretic functions is using sigma notation. So let's apply this now to both tau and sigma and see if we can come up with a sigma notation for their definition. And it turns out this is the way you define tau. You say tau of n is the sum of every divisor that divides n. We sum 1 for each one of those divisors, so that's the way we would count. We just sum 1 for as many divisors as we get. And then for sigma of n, the only thing that changes here is instead of summing 1, which counts the divisors, we sum the divisors themselves. So sigma of n is going to be the summation of every divisor of n of the divisor. So add all those divisors up is what that means. So just be aware that that there is this, I guess, special notation for sigma notation that is often used in number theoretic functions. I guess the difference here is that we can't really put an index on this because we don't know how many we're counting. We do know we're counting a finite number, so we just say d divides n to say how many, for every divisor of n, we sum some function of that divisor. So let's visualize this. Remember the definition: if we have a positive integer n, then tau of n denotes the number of positive divisors. Do you have a sense of what this is going to look like? I'm going to go ahead and plot this in the next slide. So n along the horizontal, tau of n along the vertical or the y-axis. Kind of get a picture in your head of what you think this looks like. We know that it's going to be kind of jagged. We also know that it's going to somewhat increase. Drum roll, please. Oh, sorry, that was kind of anticlimactic. So here's what the graphical depiction of tau of n looks like. So it turns out this is what it looks like. I think it's a really fascinating picture. I hope you feel the same. You can see that if tau is the number of divisors, we only have one divisor, one place, and of course that's for 1. But then we have lots of numbers that have two divisors. So I'd ask you, what are all these numbers in this row? Dramatic pause. Go ahead and answer that in your brain. And those numbers, of course, are all the ones that have exactly two divisors. So those are the primes. That row is all the primes from, I guess, 0 to 1,000. They have exactly two divisors. But really interesting, right above them is the row of all numbers that have three divisors, and it turns out that there aren't that many of those. There aren't very many numbers that have three divisors, but there's a lot of numbers that have four divisors, so that's the next one. And then again, not so many numbers that have five divisors, a lot of them that have six, not so many that have seven, and a lot of them that have eight. Not so many that have nine, but relatively, I don't know, some that have 10. And do you notice there are none that have 11 divisors? This is pretty interesting. So if you're under 1,000, there's no number with 11 divisors. So I hope this is sort of making you curious about, well, what's going on here that we have a propensity of even divisors, propensity, at least among the first 1,000 integers, to have numbers that have an even number of divisors, and I guess it's really kind of hard or rarer for a number to have an odd number of divisors. So I'll leave that up to your sort of imagination for now, but we're going to answer that by the end of the chapter, I hope. But one question I've had curiosity about forever is what is this limiting function? In other words, what is the governing function here that tells me, given a number n, what's the maximum number of divisors that n can have? Sure looks like there's an upper limit, and what I know now is that is only being recently studied in the last few years. We know a lot more about the average number of divisors. So if you imagine sort of averaging, let's see, the first 200 numbers in here and plotting that, and then averaging the first 400 values of tau, and then averaging the first 600 values of tau. And we know that's the average is actually quite a ways down below here, because we have lots and lots of numbers that have small numbers of divisors and not so many that have large numbers of divisors. So there's quite a bit known about the average number of divisors, but in terms of this upper bound, they continue to improve, I guess, estimations of that upper bound, but nobody really knows what it is for sure, and it's never been proven to be approaching a certain value in an exact sense, just in a limited sense. So that's what tau looks like. We should probably look on and take a look and see what sigma looks like. So remember that the definition for sigma is that it's the sum of all these divisors for any number n. And what would a graphical depiction of sigma look like? So I'd invite you to kind of think that over in your brain a little bit. What would this thing look like in your opinion? And it turns out that that's what sigma looks like for the first 1,000 integers. So it's kind of this spray. But what's neat about sigma, of course, is that there is some lower limit, and that lower limit, of course, is n plus 1, right? So in other words, every number is going to have at least itself as a divisor and 1 as a divisor, so those are the primes, and that means that for any number, sigma of n is at least n plus 1, right? So this line right here is, I guess that's the bounding line on the lower end, is equal to n plus 1. But of course, numbers can have large numbers of divisors other than 1 in themselves. So you kind of think of sort of these numbers up here as being the ones that are really highly composite, meaning that they have lots and lots of divisors that add up to large sums. You can also think of this line that's sort of emanating here as all the primes. And one of the things I've always been fascinated by is that there are kind of these lines that you can see through the data that must correspond to certain groups of numbers, and I'll just sort of leave that up to you to think about for right now. But you can see sort of shadows in there of the prime line down here that kind of, I guess, go through the middle of the spray of dots that is sigma. We won't reveal too much about that, but I hope that I've at least piqued your interest by looking at these plots. It's surprising that your textbook author doesn't pay any attention to this type of a display. So I think it's kind of a fascinating picture. So let's go ahead and generalize divisors now, and this is the meat of what I want to present today, and that is that if you have a number n, then it can have some prime factorization. Let's let it have the canonical prime factorization where p1, p2, and pr are all the prime bases. k sub 1, k sub 2, up to k sub r are all those exponents associated with each of the prime bases. Then it turns out that the positive divisors of n are precisely those integers d of this form, where d is the p1, the p2, the pr, so all the same prime bases, but the exponents are a1, a2, up to ar, where those a sub i's, if we go to this next line, are all either 0 or in between 0 and k sub I, where the k sub I is the exponent on the number, on the prime base in the number n itself. So in other words, this a sub I in this particular factor has to be either equal to 0 or it's some number less than or equal to the k sub I in this prime factor. So let's go ahead, and I think the best way to do this is to do an example first. So let's do an example first and then we'll prove it. So let's do this example. If we have this number 204, let's find every positive divisor of 204 using the prime factorization. So 204, let me get to my page, is equal to 2 to the second times 3 times 17. So that means every divisor of 204 is going to be some combinations of 2's, 3's, and 17's, where there are 0, 1, or 2 2's, there are 0 or 1 3's, and there are 0 or 1 17's. So here's what we do. We say, well, let's just take a look at the case where we take 2. Let me think about this really quick. So 2 to the 0 times 3 to the 0 times 17 to the 0. Well, that's certainly a divisor of 204. That's 1. Now let's take them each one at a time. 2 to the first times 3 to the 0 times 17 to the 0. So that's 2. 2 to the 0 times 3 to the first times 17 to the 0. That's 17. 2 to the 0 times 3 to the 0 times 17 to the first. So that, oh, sorry, this one should have been 3. And so that would be 17. So that would be one, I guess, way that we can write this using sort of the theorem. The theorem says that all the divisors of 204 will be some combination of these bases, just so long as the exponents don't grow larger than the exponents that are, I guess, provided in the number itself. So that's where one of them is chosen. Let's try the next one where we choose 2 different ones. So how about 2 to the first times 3 to the first times 17 to the 0, so that'll be 6. 2 to the first times 3 to the 0 times 17 to the first, so that'll be 34. And then 2 to the 0 times 3 to the first times 17, so that will be, let's see, 3 times 17 is 51. Okay, so that's choosing 2 of them. So now let's see what happens if we choose 3 of them. So how about 2 times 3 times 17 all to the first? That works, right? So that's going to be equal to, well, that's just the number, 204. What about if we had 2 to the second times 3 to the first times 17 to the 0? So that's going to be 4 times 3 or 12. So it looks like this is a multiple of 12. We could also do 2 to the second times 3 to the 0 times 17 to the first. Oh, and I got that wrong. This is not 204. It's 102, isn't it? Sorry. You can tell I'm not watching my notes. Let's see. So 4 times 17 is going to be 68. So you can see we chose 0 first. We chose 1 here, we chose 2 factors here, we chose 3 factors here, and all the different ways we could do. So the last thing we can do is just choose all 4. So we'd have 2 to the second times 3 to the first times 17 to the first, and that is our 204. And I would posit that that's it. I mean, we are done here, and the reason we're done is because if this is the number that we're trying to find divisors of, then all the divisors have to be some, okay, let's just say it, a subset of the number's prime factorization, right? That subset can include the empty set, and it can include the set itself, right? The set itself is a subset of the set. So in other words, divisors are just subsets of a number's prime factorization, and you can find them by just basically organizing your pick of a number's prime factorization like this. Let me just make sure if I got them all here on my notes. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Which one am I missing? Did I miscount? 3, 6, 9, 10, 11. I'm missing one of them. Does anybody see what it is? 1, 2, 3, 17. Oh, I see. I see what I missed. I missed in this case, when you're picking two of them, I could have just picked 2 to the second, right? Times 3 to the 0 times 17. So 4 was the one I was missing. Okay. All right, so now I'm confident. I think that I got them all. Matches my notes at least. And so hopefully that gives you a sense of how we're going to prove this. A number's prime factorization tells us just exactly what its divisors are. So let's go back and prove this, and we'll end with this proof. So I'll go ahead and write this down. Well, maybe I might as well. So here's our hypothesis. I'm going to write this down on myself. So if n is equal to p to the 1, k to the 1, p to the 2, k to the 2 times all the way up to p to the r, k to the r, is n's prime factorization, then all divisors are of form d equal p to the 1, calling it a to the 1, p to the 2, a to the 2 times p to the 3, a to the 3, where 0 less than a sub I less than or equal to k sub I for I equal to 1, 2, 3, all the way up to r. All right, so I've got the hypothesis written. I can go ahead and switch over. And what does our proof look like? We proceed directly. First, note that if when d is equal to 1, then so in other words, when d is equal to 1, all of these guys have to be 0, right? a1 equal to a2 equal to all the way up to a, and I shouldn't have done 3 here, right? Should have done r there. I don't know why I put 3. A sub r, all of those have to be equal to 0. And also, when a1 is equal to k1 and a2 is equal to k2, and I guess we'll just say dot 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 a r is equal to kr, we get that d is equal to n. So in other words, if all of these a sub i's are equal to the k sub i's, well then d itself is equal to n, and both d equal to 1 and d equal to n, of course, are divisors. So we definitely get those two divisors by applying this form. So the next thing we do is we look at everything in between. Next, assume d is not equal to 1 or d. Sometimes this is called a non-trivial divisor. So then we know that if d divides n, then d times some d prime must be equal to n. Some d prime in z, and also d prime's got to be greater than 1, right? And d is greater than 1. I guess I should write that, d greater than 1 both. So we're just talking about positives only. Both d and d prime have some prime factorization. And that is unique. And that's the FTA, the fundamental theorem of arithmetic in there. So we could kind of think of it this way. D is equal to some Q1, Q2, all the way up to, so let's say some QS, and D prime is equal to some T1, T2, all the way up to some Tn, let's say. And I'll just say where the Q sub i's and the T sub i's are primes, and not necessarily distinct, right? You could have two 2's or, two 7's here. I'll say not necessarily distinct. So then what happens is in D, and what we get here is we get that n, which we're told is this p1 to the k1 times p2 to the k2 times all the way up to pr to the kr. It also has to be equal to the product, right, of these two. It has to be q1 times q2 times all the way up to qs times t1 times t2 all the way up to tn, right? So this is one prime factorization of n, and this is another, right? Factorization of n, and this is another question mark, right? So you're getting the picture where this is going, I hope. Can there be two distinct prime factorizations of n? Well, no, there can't be, right? So since the FTA guarantees only one prime factorization of n, each prime q sub I, let's call it, must be one of the p sub i's. And maybe we call them p sub j since we don't want the same index. So let's collect those. Collecting equal primes into single power, I'll call it integral power, we get that d must be equal to q1, q2, all the way up to qs. That has to be equal to p1 to the a1, p2 to the a2, all the way up to pr to the ar, where each a sub I has to be greater than 0 or equal to it, but strictly, it could be equal to the k sub I, right? So in other words, each one of these primes can only appear, let's say if two of them were p1s, could only appear two times if there were two, I guess, if there were two p1s to give in the original, I guess, prime factorization of n. And this is for what I equal to 1, 2, 3, all the way up to r. So that's really it. I mean, that proves the forward direction that anytime we have some sort of a factor of a number n, then it has another number, that it pairs with, that multiply together. If we write them all out as a sequence of primes, then the uniqueness says that this sequence of primes written in power has to be equal to this sequence of primes written in power, right? And so the part that belongs to D must be some piece of the 1, 2, 3, all the way up to r prime bases, such that those exponents are either 0 or some number less than their exponent in the number n. And that's as desired. And there is a converse. The converse, I'll just say see the book. So the converse would say that if I have some number, right? If I have some number in this form, then it has to be a divisor of that. And of course, that's pretty easy to do. All you do is you factor that number out of here, and that lowers all these exponents down by that number, which is less than that number to begin with. And you can show that then it together with what's left over multiply together to make n, which then proves that this is a divisor. And it's interesting, I noticed that I did miss our precisely. I should say precisely because it's that word that makes this an if and only if, right? Precisely, meaning that if you have a number this form, these are the divisors. If you have a number of this form, then it is a divisor of that number, right? So that's what the precisely means. It goes both ways. So for the converse, I would just say see the book, and I think you'll get the idea that you're just factoring out some power there. So what we'll go to next in the course is computing tau and sigma, and I hope that that's at least wet your whistle for thinking about, first of all, what number theoretic functions are and what the two most common ones are, tau and sigma. And I hope that you have some intuition, at least going forward, that there should be some closed form way of doing this, right? That we really shouldn't have to, I guess, do this brute force. In other words, what I'm asking you to think about in preparation is, is there some way, that given this example problem, that we could just look at this and say, oh, there's going to be 12 divisors. Is there some way that I could look at the prime factorization, and I'll give you a hint. If I could look at 2, 1, and 1 and say, oh, there's definitely going to be 12 divisors. And then even deeper, is there some way that we could look at, all of this, the 2, the 3, the 17, the 2, the 1, and the 1, and compute what the sum, right, of all these divisors are, without having to brute force go and find every single one of them and add them all together. And so we're going to leave that for the Friday when I return. I hope that I've at least piqued your curiosity and maybe even given you some intuition about where we'll be heading next. Okay, I'll see you all on Friday. Thanks for watching the video.